reduction reactions, right? Oxidation, and that's just the basis of the kind of reactions we'll see once we start talking about the Krebs cycle, right? Usually we talk about it in the second semester, and it becomes, there's a lot of stuff in anatomy and physiology. So you gotta put in the time to kind of read up on it, especially if you haven't read it before. Oxidation reactions, you have oxidation, which is loss of an electron, usually means loss of hydrogen, right? When you lose a loss of an electron, loss of a hydrogen by a substance, you can either oxidize by losing that hydrogen or gaining an oxygen. Again, when we gain an oxygen, oxygen is so electron hungry, it will try to steal electrons for itself. So when we oxidize something, you have less electrons. Reduction is a gain of electrons, usually by gaining hydrogen, or the opposite, right? Or loss of oxygen. These reactions allows us to have synthetic and decomposition reactions. Now, the good news is that's about all I'll talk about in terms of the chemistry, in terms of that type of chemistry. The bad news is, we still have to talk a little bit about chemistry. Now, there's, some of you might have known the difference between organic and inorganic chemistry. Inorganic chemistry is general chemistry, and with general chemistry, usually it's things that does not contain carbon, right? So when we talk about hydrochloric acid, that kind of stuff, and you're mixing it with, some kind of salt, that is general chemistry. The main basis that we'll talk about, though, is this, organic chemistry. Organic chemistry is organic because it contains carbon. And this is important because most of our biochemicals are made out of carbon, because we're made out of carbon. Okay. What makes water special? Water is special because of the hydrogen bonding, right? It's got cohesion and adhesion properties. We find it just about everywhere in our body. It's found in 90% of our blood. Most of our blood is plasma, right? Plasma is going to be where we find the sodium, the potassium, all the hormones that our blood carries. Well, they're not found where the red blood cells are. They're found in the liquid part of your blood, the plasma. Now, their red blood cells and white blood cells are important, but they make up a very small amount of your whole blood. So when I take blood out of your veins to test it, to measure the iron, to measure the hemoglobin, to measure if you're anemic or not, well, we are going to measure different parts of your blood, right? There's two main components, plasma and cells. Well, the plasma where you just found everything else. When you take your blood glucose level, where's the glucose? In the plasma. All right, so the plasma is very important. Now, when people also have surgery and they start to bleed, what happens is we can give them packed red blood cells so that they can carry more oxygen. Or we can give them plasma. The blood bank will accept both and they'll separate it. So then you can give one versus the other. So water is inside the cells and between the cells. If you've ever had your foot swell because you've been on your feet so much at work, well, that's water that's kind of moved in between our cells in the area we call the interstitial space. That allows you to have edema. So water is found just about everywhere in our body. Now, water is very important because of this as well in our body. It has a high specific heat, therefore requires a lot of heat to raise the temperature of water, allowing us to stabilize our body temperature. So then when you go outside and it's negative 20 degrees outside, your body temperature doesn't drop to negative 20 degrees over a course of many minutes, right? It allows us to stabilize it. If it's so hot, like in Arizona, or God forbid, Florida in the middle of summer, and it's hot and humid, well, our body temperature will increase but not to the same level as we see in the environment. Now, we will also later on talk about why most of us prefer to have dry heat versus that wet, humid heat that kind of makes you feel sticky, right? Why most of us prefer the dry heat. Water acts as a lubricant in our body and participates in a lot of chemical reactions in our body. Okay. In terms of mixtures, and we do see these in our body, right? We have suspensions and colloids. Know the difference for the quiz. Suspensions are materials that separate unless stirred. Think of fresh squeezed orange juice. If you've ever gotten orange juice from Sendix and it's freshly squeezed, the pulp actually rises to the top. So in order to just make sure you drink orange juice and not eat pulp, you have to mix it. Now, I use this example as well. Some of you guys have kids. When kids get sick, we can't just, especially babies, you can't just give them a big antibiotic pill and make them swallow it, right? So how do we give the antibiotics? We dissolve it in water. But antibiotics that kids get is a suspension. So if your kid is sick, what happens is, in the pharmacy, they have like the dry form. And then the pharmacist will add water to it and shake it up. If you would then give that medication to the baby, you use a syringe and dry it out, well, the pharmacist just shook it. So all of the antibiotic medication has equally dispersed. So if I take a little bit of the antibiotic solution from the top, I'll have 5 milligrams of that antibiotic. If I do it all the way from the bottom, 5 milligrams of antibiotic, because I've equally mixed it apart. Now, with antibiotics, if you let it sit, and now you might need 2 doses, one in the morning, one at night. It's been a few hours, now you need the nighttime dose. If you let it sit, all of the heavier antibiotic molecules start to fall to the bottom because of gravity. If I would take the syringe and remove some of the liquid from the top, well, most of the antibiotic medication has fallen to the bottom. So you're not giving as much as you think you're giving. So every time you have to give your kids antibiotics, and it's in a liquid form, you have to shake it each time. So then you have equal dispersion. A colloid is something you don't have to mix. So a big example here is think of orange juice versus milk. Now, I know sometimes people shake milk. You don't need to shake milk. Milk is always equally dispersed because of the amount of fat that's found there. Our blood is a combination of both. Right, the colloid is the actual red blood cells that can separate, and then the suspension is all the mixing of the salts that we see in our body. A solution is a mix of liquids, gas, or solids. The solvent is usually the liquid part in our body. It's almost always water. Solvent will allow you to dissolve things. A solute, and we do use this term a lot, a solute is any solid that dissolves. So it can be a salt, it can be a protein, it can be, right, a hormone that can go into that water in our bloodstream, the plasma, and then dissolve in it. The only thing it can't be is fat. Fat and water, oil and water don't react. They don't dissolve into each other. They separate. Everything else does. The sodium chloride we see in our body, the bicarbonate that we see, they can dissolve directly into the plasma of our whole blood. Again, whole blood is a combination of all of this. It's a mixture, it's a suspension of colloid and a solution. Right, solute, you're gonna see, I use, how do we measure the concentration of things? Well, you guys remember molar mass and then volume, things like that. I just want you to understand that there is a unit that we use specifically for amount of salt, amount of solutes that is dissolved in water. Right, for our body, we need some way to kind of measure how much salt, protein, everything, right? How much of it is dissolved in your plasma? How much of those salts and proteins are found inside your cell and then in between the cell. We need to be in equilibrium. So what happens is, when we measure the concentration of a salt or a protein, we can either use these two terms, osmolality or osmolarity. They're basically the same thing. They measure the number of particles of that salt found in 1 kilogram of water versus 1 liter of water. Now, medically, we use osmolarity and we use liters. Why? Simple. When you guys probably go to the ER, and sometimes you kind of go with a friend and they're dehydrated, right? What happens to dehydrated? They don't just give you a liter of water and tell you to drink it, because you could do that at home, right? So what they do usually is give you bagged saline through an IV. That saline is 1 liter already. You don't have to measure it, it's assumed to be 1 liter. So we already have that unit right here in osmolarity. Right? Now, the dumb thing to do is kind of switch it to this. You take that unit, that bag, and then you want to go and find a scale and weigh it. Right? That's kind of stupid, right? So what happens is, when you have time, if you're in the lab and you have time to weigh it, then we use this term to measure concentration of salt in water. We use osmolality. But if we're in the field, we're on the wards, you don't have time to be weighing every bag, especially when they give you the unit right on the bag. So we use osmolality because of the fact that they already gave you that 1 liter, right, the amount of solutes per liter already, and it's written right on the bag. Now, in our body, we don't really use whole numbers here, right? We use small numbers, milliosmoles. And second on, we'll kind of discuss why we need to be in equilibrium. So the average kind of solute concentration in our body, that means all the sodium, all the potassium, all the chlorine, all the bicarbonate, right? All of those proteins usually add up to 300 milliosmoles of solutes found in your blood, found inside your cell, found between your cells. One more second. All right, so in terms of acid and bases, what's the difference between acid and base? There's going to be a lot of different definition. Some of it, you might have heard of Bronsted-Lowry, right? Definition for it. The one that we'll use is just very simple. An acid is anything that can give hydrogens. So some of you might have heard of carbonic acid. When we see carbon dioxide being produced in our body, we have to get rid of that carbon dioxide. What do we do with the carbon dioxide and the water? We're going to turn it into this. This is carbonic acid. And what carbonic acid does that's pretty special is that it can turn and become an acid. When you push the reaction to the right, this has an extra hydrogen. It can give the hydrogen away. So it can be a weak acid. But this guy right here, it's got a negative charge, right? So an acid can give a hydrogen away. This molecule, carbonic acid, it can give a hydrogen away. Well, once we form the byproduct, this HCO3 minus, what happens? That's a base, right? A base is anything that can accept a hydrogen. So if we have too much hydrogen in our body, it can react with it. Oops. It can react with that hydrogen and reform carbonic acid. In other words, it can act as both. This carbonic acid can act as both an acid and a base. When you have one that can act as both, we call it a buffer. Right? A buffer is a substance that can remove and give electrons or give hydrogens, and it can receive hydrogens as well. When you receive hydrogens, you act as a base. Right now, there's all these reactions. You guys know hydrochloric acid is kind of scary, right? But when you add to it sodium, all right, when you add hydrochloric acid and you add it with a base, NaOH, sodium hydroxide, what happens? The acid always reacts with the base right here. So you have water and salt, right? Showing us that when we have a strong acid reacting with usually a strong base, we produce salt water. It's kind of weird, isn't it? You have some really strong base that can really damage your shirt, right? It can bleach it. You have a really strong acid that can damage your skin. And when you add it together, well, because of the way the reactions work, all you make is salt water. Kind of crazy. Yes?
So if we drink salt water, we can create acid in our body?
Usually not, right? Now you're gonna have a lot more issues if we just drink pure salt water. But when we are looking here, is you can't get this reverse reaction without help. So it's not like you drink salt water and then you turn into hydrochloric acid. You need a little bit more steps. So in terms of this happens as well, this reaction. It even needs a little bit of help, right? So we have enzymes that help it remake itself, right? So usually when we talk about these reactions, you can see it out of the body, in the body. Some of these reactions need a little catalyst to kickstart it. Now, if you look at the pH scale right here, remember that the stronger the acid, the lower the pH. And the reason why is because of the way we get the value for pH, right? pH is, I know I'm gonna write it and you guys are gonna freak out because I'm gonna use the word log, right? pH is the negative log of your hydrogen concentration, right? Meaning that if my hydrochloric acid or the hydrogen concentration, right here, if the concentration is 0.1 moles versus 0.001 moles, well, obviously this one, 0.1 is bigger than 0.001, right? So if it's bigger, this one should be more acidic. How does it work? Like this. pH equals, right? When you look at a mole of hydrochloric acid, or 0.1 moles of hydrochloric acid, that means you have 0.1 moles of hydrogen, and now you're gonna react it with 0.1 moles of chlorine. They react together to form hydrochloric acid. You need equal amounts, right? Because you only have one hydrogen reacting with one chlorine. So what happens? By saying it's 0.1 moles of hydrochloric acid, I know the concentration of hydrogen in that solution. That is, the hydrogen concentration is 0.1. And this one, 0.001 moles. Well, it means you have 0.001 moles of hydrogen reacting with 0.001 moles of chlorine, right? So we'll know the concentration of that as well. Now, log sounds scary. All log is just a number of zeros we have. What's the log of 1? How many zeros? None. 0. What's the log of 10? How many zeros? 1. The log of 100? 2. See how that goes? Log of 1,000? 3. Just count the zeros. Now, what is the log of 0.1? Now we go into negative numbers. Negative 1. Log of 0.001 or 0.01. Negative 2. Right? Kind of easy, right? So what happens? Well, the log of 0.1, negative 1. That's the log of 0.1. We take the negative of that, the two negatives cancel, my pH is 1. Strong acid, right? We know that because of the concentration. How about if the concentration is 0.001? We know it should be a weaker acid, right? But let's see how we find that out. We find it out by doing the exact same thing. pH equals negative log of hydrogen concentration. Now we're doing this one. We just mentioned, right? By saying they're equal, you have 0.001 moles of hydrogen reacting with 0.001 moles of chlorine. So the hydrogen concentration is 0.001. What is the log of 0.001? How many zeros? 1, 2, 3. Actually, it should be negative 3, right? Log of 0.01, negative 2. Right? So the log of 0.001 is negative 3 because we're going in the opposite direction. And now we take the two negatives, they cancel. The pH of this solution now is 3. Makes sense, right? That this solution, it's got less hydrogen, is less acidic. This solution, right, 0.1 is bigger than 0.001. So this solution of hydrochloric acid, it's got greater numbers of hydrogen, makes sense that pH will be lower, making it a stronger acid. There's an inverse relationship. As the amount of hydrogen goes up, the pH goes down. The more hydrogen, the lower the pH, the stronger the acid. The weird thing is you would think that our pH in our body would be kind of, neutral, right? Very neutral. The pH of our body is actually slightly basic. So keep that in mind. Almost done with this.